Hi there, welcome to my channel. In this video, I'm going to discuss about the solution for minimum genetic mutation problem. Let's look at the problem description. A gene string can be represented by 8-character long string with choices from A, C, G, T. And there is also a gene bank that records all the valid gene mutations. A gene must be in the bank to make it a valid gene string. So we are given a 2 gene string, start gene and end gene, and the gene bank, and we have to return the minimum number of mutations needed to mutate from start gene to the end gene. If there is no such mutation, then we have to return -1. The starting point is assumed to be valid, so it might not be included in the bank. Okay, let's take a look at the example 1. So the start gene is AACCGGTT. End gene is AACCGGTA. The last letter is changed. The end gene string is present in the bank. The number of mutations from the start gene to end gene is 1. So only one character change will lead to the end gene string. So in the case of example 2, the start gene is AACCGGTT and end gene is this, and the bank has 3 strings. So from this string to, if we modify the last T to A, we get this string, so that is one mutation. And then if we modify the third letter C to A, we get the end gene, which is present in the gene bank. So number of mutations needed to move from start gene to the end gene is 2. And the constraints are the bank length is ranging from 0 to 10, and start gene and the end gene's length and the gene string in the bank all are of size 8 bytes. And the start gene, end gene and the bank of I consist of only the characters A, C, G, T. Let's look at the approach to solve this problem. And for this input, the number of mutations is 2 to move from start gene to end gene. We can model this problem as a graph problem, and in that each gene string is a vertex, and the neighbors are all the gene strings present in the bank which are differing only one character from the current string. Okay, for example, in this input, the start gene is AACCGGTT, so that is the start, and its neighbors strings are, there is only one that can be a neighbor of this string, that is AACCGGTA. So the string which the last character is modified, between the start and this only one character is modified, so this is a valid neighbor for the start gene. But all other strings are differing more than one character, so they cannot be a neighbor. So that's why there is a link from the start gene to the this gene. And for this gene, what are all the valid neighbors? So if we take a look, the second string, right? So AACCGCTA. So if we modify this character, then we get this string. So this is a valid neighbor for this string. Same way, AAA. Okay, so if we modify the third character C to A, we get this string. So these two strings are valid neighbors. So that's why we have the edge from this string to the other two strings. So this is a graph. So how do we find the minimum number of mutations? If we do perform the breadth first traversal on this graph, we can get the minimum number of edges that takes us from the starting gene to the ending gene. So that's what I listed here. So this can be viewed as a graph, and each gene string is a vertex, and the valid neighbors are the gene which are differing only one character. And if we do perform the breadth first search, we can get it. In order to get the perform the BFS, we need to get the list of neighbors for a given vertex. So every time whenever we visit a node, we traverse this bank and find all the strings which are differing only one character with the current vertex. Let's look at the flowchart. Input for this procedure is start gene string, end gene string, and the bank of genes. First we check whether the bank contains the start gene. If it is not, then we add the start gene to the bank. Then we initialize the visited array and the distance array, and then the queue, which will be used by the breadth first traversal algorithm. Then we initialize the minimum distance variable to -1. Okay, because we have to return -1 if there is no such valid mutations. Then first add the start gene to the queue, and then mark that vertex as visited. So here what I'm doing is instead of using that string, I use that index in the bank array as the vertex. Okay, so we add a 0 to the queue and we mark that 0th element in the visited array as visited and initialize the 0th element in the distance array with the value 0. Then the outer for loop is entered. This outer for loop runs as long as there are some elements in the queue and the minimum distance is equal to -1. Okay, so first in the outer loop we dequeue the element from the queue and get all the neighbors of that dequeued element. Then we iterate over that neighbor list, and for each neighbor we check whether that is already visited or not. If it is not visited, then mark it as visited, then update the distance of the neighbor node. So basically we have to add 1 to the distance of the parent node, which is the current, the dequeue element. Once that is done, then we check whether that neighbor is a end gene string. If so, we assign that distance of the end gene to the minimum distance variable. This will break this outer loop. Because of this condition, it will break the outer loop and we come out and we return the minimum distance. If we don't see any valid transition from the start to end gene, then we will end up the situation where the queue is empty but the minimum distance is still -1. So when the moment we have the queue empty queue, then we come out and return that -1. Let's move on to coding. First I define the constants for visited and not visited states. Inside the mutation function, I define the minimum distance and initialize that with -1, and then the start found boolean with false value. Then I check the edge cases where the bank is empty. In that case, I check whether the start gene and the end gene are same. In this case, I return 0. Otherwise, I return -1 because the transition is not possible. Next, I check whether the start gene is present in the bank array. If not, I add it to the beginning of that array. We have to make sure the start gene is also present in the bank. Next I initialize the visited array and the distance array. Next I initialize the queue, which will be used during the breadth first traversal. I initialize the queue with the first element. So basically, instead of using the gene string, I use the index of that gene string in the bank array. So I added the start genes index 0 in the queue, and then I mark that as visited, and then I set the distance of that vertex is 0. Then I write the outer for loop. This for loop runs as long as there are some element and the minimum distance variable is not set. So inside that for loop I dequeue the element from the queue. Which gives the index of the current element in the bank array, and then I updated the queue. Then I get the current gene strings value from the bank array using this index. Then I make a call to the get adjacency list to get all the neighbors of this current gene. Basically this function will return all the genes which differ only by one character. Once we get the neighbors list, I traverse all the neighbors if they are not already visited. So first I check whether that neighbor is visited already or not. If it is not visited, then I mark that as visited and add that neighbor to the queue. Then I updated the distance of the neighbor from the starting node. So basically I add 1 to the distance of the parent node. The parent node is pointed by the IDX. Then I check whether the current node is the last gene. In that case, I set the minimum distance value with the distance of the neighbor, current neighbor, and break out of the loop. Then finally I return the minimum distance. Next I am going to implement the get adjacency list function. This will take the current gene and then the bank array. It will return an array of integers, which is an array of indexes. I traverse the bank. I check whether the each element in that bank array differs only by one character by calling the isValid mutation function. I initialize the neighbor slice, which is a slice of int. So if it is a valid mutation, then I add the current index to the neighbors list. Next I'm going to implement the isValid mutation function. This will just compare the two strings and check whether they are differing more than one character. If they differ more than one character, it will return false. Otherwise, if it returns if it differs only by one character, then it will return true. Otherwise, it will always return false. So I traverse all the characters in the gene string, compare each character. The moment I see there is a difference, then I check whether the current diff count is already 1. In that case, the next time when we increment, it will obviously more than 1. So I return false even before incrementing the diff count. After coming out of the loop, I return if diff is exactly equal to 1. So that way we make sure if it is 0 or if it is more than 1, both the cases we return false. Next I'm going to run the test cases. Oh, 3 test cases are failing. Let me take a look. So when we traverse the neighbors, we have to compare the end gene with the current neighbor instead of the currently dequeued node from the queue. So let me rerun the test case. Okay, all the tests passed. Next I am going to submit this program. Cool, this program is accepted. Next I am going to do the code walkthrough with sample input. Let's do the code walkthrough for this input. For this the expected output is 2 because the starting gene mutate to this by changing the last character and then mutate to this by changing the third character from C to A. So 1 and 2. So that's why the expected output is 2. Okay. So first the minimum distance is initialized with -1. Then next what we do is we check whether the bank is empty. In this case it is not, so we skip. And then we check whether the start gene is present in the bank already. In this case the start gene is not present in the bank, so I added that to the bank. So that's what this for loop is doing. So if it checks whether the start gene is present, if it is not present, it will add the start gene to the beginning of the array. Okay. Then I initialize the visited and the distance array with the size of the bank, and then initialize the queue with the index of the start gene in the bank array. So basically I use the index of the gene string in the bank array as the vertex. Okay. So first I add the index of the start gene to the queue and mark that as visited, and then the distance of that particular vertex is 0. So that is what we are seeing here. So this vertex is visited. Then we enter the outer loop. Okay. So in the outer loop we dequeue the first element from the queue, which is 0, and assign that to the index variable, and the queue becomes empty. Then we use that index into the bank array and get the current string, which is the start gene. So that's what we are seeing here. And next we get the neighbors of the current gene. So we call the get adjacent list, which traverses the bank array, and then it will add the gene string in the array if that differs by one character. So this, we call this function is valid mutation, that will check whether the current string and the gene string from the array bank is differing by only one character and return true. So whichever gene string differs by one character, that gets added to the neighbors list. Okay. So in this case, for the start gene, we see only this gene string differs by one character. So that's why we see the neighbors list contains only a single entry, which is the index 1 in the bank array. Then in the inner loop, then we enter the inner for loop, which traverses all the neighbors. It checks whether that neighbor is visited already or not. So in this case, node 1 is not visited yet, so we mark that as visited, and it's not visited, and I mark that as visited, and then update the distance by adding the distance of its parent plus 1. So we update the distance of the node 1 as 1. Because we have only one neighbor, after processing that neighbor, we come out of this inner loop and we go back to the outer loop, which dequeue the element from the queue. In the now we have the vertex 1. Okay, then for this we get all the neighbors. So in this case, the index 0 also differs by one character with respect to when we compare with this gene string, and the second and third gene string also differ by only one character. So all these three are neighbors of the first gene string. So that's why we see three neighbors, 0, 2 and 3. Then we traverse the neighbors list and check whether each neighbor is visited already or not. First we get 0, which is already visited, so we skip this, and then next we take the neighbor 2, which is not yet visited, so we mark that as visited, and then add that to the queue. So we have that, we see that in the queue, and then we update the distance of that node 2 by adding 1 to its parent's distance. In this case, the distance of the vertex 1 is the parent of the vertex 2, so we add 1 to this and get 2. And then we check whether that current neighbor is a end gene. In this case it is not, so we go ahead and process the next neighbor, which is 3. So in this case we check whether the 3 is already visited or not. It is not visited, so we mark that as visited, and then we update the distance by adding 1 to its parent, so we get 2, and we update the distance as 2. We update the distance of 3 with value 2. Next we check whether the current neighbor is the end gene string. In this case it is. So we set the minimum distance variable with the value of the current neighbor's distance, which is 2, and we update that. And once that is done, we come out of the inner loop and we go back to the outer loop. Here the min dist is not equal to -1, so we break out of this loop and then we come out and return 2. So minimum distance is 2, and that is the expected output. Next I'm going to do the time and space complexity analysis for this solution. Let's do the time complexity analysis for this input. So in order to compute the number of mutations, we have to traverse all the 4 nodes or the gene strings present in the bank. So this plus the start gene 4. Okay. So at most we traverse n vertices. Sometimes we may find the transition early. For n number of gene strings, we have to traverse all the n gene strings. So the time complexity for this solution is order of n. So the breadth first traversal algorithm makes sure each node is visited only once. So the time complexity is order of n. And with respect to the space complexity, we need to allocate space for visited and distance array, which is equal to the input size. So, and then the queue size is depending on the number of genes in the next level. For sometimes it may go up to n minus 1 element. So the space complexity is order of n. Thanks for watching this video. Have a great day.